This system can modify the compression of an engine while it's running. We'll analyze how it works. The compression ratio of an engine is directly related to the performance and power it can deliver. If we increase it, the engine will be better, although the fuel to be used must be of higher quality. However, turbocharged engines have less compression than naturally aspirated engines, because when the turbo blows air, the cylinder fills more, and with more air, the real and dynamic compression of the engine rises. Additionally, when a turbocharged engine is running at a low load, such as when driving at low speed or simply idling at a traffic light, the turbo does not work and the engine is affected by low compression. This causes turbo engines to consume more fuel in these situations, which in daily life occur 90% of driving time. Now, if we could modify the compression ratio according to the load the engine is carrying, the problems will disappear. The VCR Conrod is currently being tested on a BMW 240i, which is driving around on the streets, but how did this idea start? In 2013, Professor Dr. Carsten Wittek took charge of the piston machine laboratory at the Hochschule Heilbronn University located in Germany. Wittek knew that just as variable ignition timing or variable camshafts were invented in the past, now the turn of variable compression had arrived. So he got to work and with his team and partners developed a variable length connecting rod. This VCR connecting rod can rotate the pinhole eccentrically to raise or lower the piston, increasing or decreasing compression. Let's analyze in detail how it works. First, we have a crankshaft that looks normal, but is actually modified with an extra oil passage. The original passage is responsible for bearing lubrication as usual, while the additional passage is only pressurized as required by the ECU. This oil will pass to the rod cap through the green channel and move a blue valve. When it's pressurized, it pushes the valve, and when not, the spring pushes it back. In this way, oil is sent through the desired channel. Then we have the connecting rod, which, as you can see, has two internal cylinders. In the wrist pinhole, we have this moving part with an eccentric hole. This part was named epsilon. When epsilon rotates, the off-center hole moves up or down. Epsilon is attached to two mini pistons that run through the cylinders of the connecting rod. When a piston is pressurized with oil coming from the crankshaft, the bore rises and lifts the piston. Epsilon must be maintained with good oil pressure to keep the piston up. Otherwise, with the normal movement of the engine, which is constantly going up and down, epsilon would turn by itself and the piston would go down, especially when the combustion stroke occurs. The other piston does exactly the same, but in reverse. It is responsible for keeping the piston down and must be strong when the piston reaches top dead center, since at this moment it stops completely and then begins to go down. A tremendous force that occurs particularly at high revolutions. In the first step of the project, the additional oil channel did not exist and a moving arm connected to the connecting rod was used to carry the oil. This mechanism is called Varamot. Obviously, it added more moving parts and weight, but it was provisional until the double oil channel crankshaft system was invented. With the eccentric operation of epsilon and its levers, the force required to keep the piston up is very low. Only 3 bar of oil pressure is enough to keep epsilon in the desired position, and 3 bar is the standard pressure of a combustion engine operating at 3,000 revolutions. On the other hand, when an engine is at 1,000 RPM, the oil pressure is barely 1 bar, and that would not be enough to keep the piston up. An independent electric oil pump is required to always maintain 3 bar regardless of engine RPM. Another VCR rod model works in a very similar way, but now uses a gear inside. The gear is also actuated in the same way as before, and when the mini piston is driven by oil, the rack moves and rotates epsilon, lowering or raising the piston. However, this system was not used and the first one remained. After years of research and development, in 2016, a BMW 240i F22 with a manual transmission was added to the project. This car is equipped with a 3-liter 6-cylinder engine which generates 340 horsepower and 500 Newton-meters of torque. The compression is 11:1. Its 6 connecting rods were replaced, and as for the crankshaft, instead of drilling new oil passages, it was preferred to use a mobile actuator located in the crankcase. At the rod cap, the internal valve has a protruding part that, when it passes through the actuator, it hits and operates, eliminating the need for the crankshaft oil channel. Its oil pump was modified to always maintain at least 3 bar or 43 psi and be able to operate the mechanism. Its compression ratio can easily vary between 9.7 and 13 to 1. It went through tests on the dynamometer, and finally, for 2019, the 240i hit the streets and started rolling. Higher turbo pressure and power can be achieved by lowering the compression from the original 11 to 9.7. It also allows it to operate with lower quality fuels. And at low speeds, which is 90% of the time an engine runs when we go to work, the advantage of higher compression resulted in a real saving of 5% in fuel. Additionally, a small 3-cylinder engine from a Ford Fiesta EcoBoost was also modified, and lab tests were carried out, but with the first crankshaft hydraulic system mentioned at the beginning of the video. Let's move on to the disadvantages of the engine. The connecting rod is more complex and has internal moving parts that could get stuck. The connecting rod is weaker than the original. It has a complex shape and hollow parts. The connecting rod is heavier, so it could limit the maximum number of revolutions. The gear system has a rack that comes out of the connecting rod and invades the space of the piston. A modified or electric oil pump is required, and by always operating at 3 bar, it increases engine losses by having to work harder. On the other hand, we have advantages that can justify the new system. In the event of a failure in the hydraulic system, the ECU can adjust turbo and ignition parameters by slightly reducing power and avoiding damage. The commanding system from the crankcase is easier to use in existing vehicles, while the system with a double oil vane crankshaft is better for engines to be manufactured from scratch. With the correct alloy in the connecting rod, added to a good computer-aided design, a light and strong connecting rod can be obtained, although it's a little more expensive. It improves efficiency and produces fuel savings of 5 to 8%. Simply put, the system pays for itself over time. It can operate with any fuel quality. Modifying an engine and installing this system would not be very complex. It would only require new connecting rods, actuators in the crankcase to modify the piston of the connecting rod, and ECU tuning. Finally, by 2022, research had begun to run on hydrogen, and it is expected to have the engine running by mid-2024. More information can be found on the university website. Did you know about this rod system? Leave your opinion in the comments below about whether you think this is a viable system or not. Also, don't forget to share this video with your friends and hit that like button. We'll see you in the next video.